This is the sound produced by the Soviet Union's 1957 launch of Sputnik, the first artificial satellite. Elon Musk's Tesla Roadster was put into orbit around the Sun by SpaceX in 2018. Only a few months after its launch, Sputnik plummeted back to Earth, and Elon Musk's Tesla is now nothing more than an unmanageable piece of space garbage. Such a piece of garbage. We still interact with about 1,700 functioning satellites that orbit the Earth and beyond. But how precisely do we communicate with things in space? From satellites in low Earth orbit to deep space probes at the frontier of our solar system, we will examine the various ways humans communicate with objects in this video. We will also discuss the technology that is being used and how its capabilities must increase to handle the growing volume of data we are gathering from our solar system. Consider sending a command to a satellite that is 3,6,000 kilometers above Earth in a geostationary orbit. First, the command is transformed into a radio wave, a form of electromagnetic radiation that moves at the speed of light, or 300,000 kilometers per second. Following the conversion of the order into a signal, the signal is sent to the satellite via a ground station antenna, which uses its extremely sensitive antenna to pick it up. The signal will then be translated into code that the onboard computers can comprehend by the onboard systems. In order to transmit data back to Earth, the majority of satellites have both an uplink and a downlink. NASA recognized in 1962 that the Apollo missions would require a completely new communications system. In addition to traveling far farther than the previous missions, the Apollo missions would also be transmitting live television footage and telemetry down to Earth, as well as communicating with 3 people who were working in 2 different spacecraft. They created the unified S-band system, which merged various frequencies into a single antenna to transmit television, voice, command, and telemetry data. Through fixed ground stations positioned all around the planet, this system would communicate with the Apollo spacecraft, with the exception of when the spacecraft curved around the far side of the Moon, where the signal would be lost until they reappeared on the opposite side 40 minutes later. This would enable mission control to maintain constant contact with the crew during the voyage. In order to ensure their reappearance on the opposite side of the Moon, the astronauts had to perform a crucial maneuver during this time: starting the engines. A successful burn would put the crew on the anticipated course, allowing mission control to precisely predict when they would be able to communicate with the Apollo 8 crew again. We have it. Apollo 8 is currently orbiting the Moon. In this room is a chair. This is Houston's Apollo control. I will now switch to Jim Webb's voice. Naturally, satellites in orbit around the Earth may also experience this signal loss if the transmitter's path to the satellite is unclear. In order to overcome this, NASA established the Space Network, which relays data from other spacecraft to fixed ground stations via satellites in geostationary orbit. This offers constant worldwide coverage for every orbit of the Earth. Satellites in Earth's orbit might be covered by the Space Network. But what about satellites located far away? Approximately 1.5 million kilometers is the furthest a satellite may orbit the Earth before the Earth's gravitational pull equals that of the Sun. What about satellites located billions of kilometers distant, though? The Voyager 1 space probe is the furthest man-made object from Earth. In order to investigate the outer solar system, it was launched in 1977. It is now moving at a speed of 6,200 kilometers per hour and is 20 billion kilometers from Earth. The Space Network's transmitters are not strong enough to send and receive data from satellites in deep space. To connect with satellites this far away, we require a system known as the Deep Space Network. The antenna complexes that make up the Deep Space Network are situated in America, Spain, and Australia. On Earth, these facilities are equally separated by 120 degrees. Each complex contains 2 smaller, high-efficiency antennas, in addition to a 70-meter antenna. It is generally easy to pick up satellites near Earth because they utilize low-gain antennas that disperse their signals in all directions. High-gain antennas are used by deep space satellites to concentrate their radio waves, which increases the signal power when it reaches Earth. Deep space communication systems are subject to ever-increasing pressures. More than 300 terabits of data had been returned by the Mars Reconnaissance Orbiter as of March 2016. Additionally, NASA projects that our space communications capabilities will need to increase by a factor of 10 over the next 10 years, as we continue to launch an increasing number of satellites into deep space. Therefore, it is encouraging to know that the courageous tiny spacecraft we send to the furthest reaches of our solar system can communicate with us and tell us about the conditions there as we continue to gaze farther into space. Please feel free to ask any questions you may have in the comments section below. In order to participate in the conversation as we continue to learn more about everything related to space, make sure you are subscribed. I appreciate you watching, and I hope to see you in the next video.